Okay, let's look at this question from your 8.1 homework. Notice that the reading speed for second graders is given to be approximately normal with a mean of 90 and a standard deviation of 10. In part A here, all they're asking is what is the probability that an individual student will read more than 96 words per minute? So that's just straightforward using the normal calculator on Statcrunch, or you can use the normal CDF function on your calculator. We were told that the mean is 90 words per minute. We were told that the standard deviation is 10 words per minute. And we want to know the probability of more than 96 words. So we'll switch this to greater than or equal to 96 words. Probability is 0.27425, and they want it rounded to 4 places, so 0.2743. Okay, so that one was just an individual student. So an interpretation is if 100 different students were chosen for this population, we would expect 27 to read more than 96 words per minute. And now in part B, we want to know the probability that a random sample of 10 second grade students from the city results in a mean reading rate of more than 96 words per minute. Big difference here. Now we're not talking about an individual student, we're talking about the mean score for a group of 10 students. Well, a group of 10 students, some of them would have reading scores higher than 90, the mean 90, some would have reading scores lower than the mean 90. But the mean of all 10 of them should be closer to 90. Sorry, my cat stepped on my computer. It should be closer to 90 than an individual would be likely to be. So the distribution of sample means from samples of size 10 have a smaller standard deviation than individual students would have. The standard deviation will be the population standard deviation divided by the square root of the sample. So in this case, 10 divided by the square root of 10, because our sample has 10 in it. And that gives us a standard deviation of 3.16. So the only thing changing here is that our standard deviation is now smaller. It's 3.16. And we're still looking for the probability that the mean reading rate for the 10 is 96 words per minute or more. This should be much less likely to occur because it would be more unusual to find a group of 10 students who average such a high reading score if the average is only 90. And notice it is in fact a lot less likely, 0.0288. So an interpretation for that, if 100 samples of 10, so we took a group of 10, another group of 10, another group of 10, we did that 100 times, we would expect only about 3 of those samples to have reading rates, mean reading rates, more than 96 words. It's a lot less likely that you're going to find a group of 10 students who read that fast on average than it is that you find an individual student who reads that fast on average. And hopefully that does make sense. Now in part C, we want to know if there's a random sample of 20 second graders, how likely is it that the mean reading rate is more than 96 words per minute? So what changes here? The standard deviation changes. If we're talking about a group of 20 students, it's even more unlikely that you would have a mean reading rate that high. And our standard deviation is going to be even smaller. So the original standard deviation of 10 divided by the square root of our sample size, which is now 20, is a standard deviation of only 2.236. So I'm going to change my standard deviation to 2.236 and compute. And I find that there's only a 0.0036 chance of finding a group of 20 with a mean as high as 96 words per minute. So in this case, because that is less than a 1% chance, if we took 100 samples, we would expect to find none of them that have, oops, it's the greater than one we want, top one. None of them to have reading rates, mean reading rates of more than 96 words per minute. So what effect did increasing the sample size have on the probability? Well, you're a lot less likely to find extreme values because increasing the sample size decreases the probability because the standard deviation decreases as n decreases. So it decreases the probability, the standard deviation decreases as n increases. Okay, now in part E, we're talking about a teacher instituting a reading program, and she uses a random sample of 22 second graders. Their mean turns out to be 92.7 words per minute at the end of this new reading program. Remember that mean for all is 90. So a mean reading rate of 92.7 words per minute is unusual for a group of 22. Well, let's find out if it is. So we know the mean is 90. The standard deviation, if we have 22 in our sample, would be 10 divided by the square root of 22, which is 2.132. And we're looking at how unusual it would be to find a mean greater than 92.7. Well, it looks like that occurs with probability 0.1026 or 0.1027 if we round. So that would actually not be considered unusual because if the probability of obtaining a result of 92.7 is more than 0.05, it's 0.1027. This means that we would expect a mean reading rate of 92.7 or higher from a population whose mean reading rate is 90 in 10 of every 100 random samples. It's about a 10% chance of that happening. We don't consider something unusual until it's less than a 5% chance. Okay, now in part F, we would like to know, well, if we have a group of 23 students, what would be considered unusual? What would have only a 5% chance of occurring? Well, first we need to find out what the standard deviation is if we have 23 in our sample. So we'll take 10 divided by the square root of 23. And that standard deviation is 2.085. We don't know what that mean reading rate is going to be, but we would like for there to be only a 5% chance, 0.05 chance of falling above it. If you leave the X portion blank and put in 0.05 for the probability and hit compute, you'll find out that the mean score for the group of 23 students that has only a 5% chance of occurring at that value or above is 93.43. So 93.43 words per minute or above would be considered an unusually fast reading rate.